think we can start. Good morning, everyone. Thank you for coming on such a nice day outside. So, today we will have the fourth and the fifth lecture from the AURALIZE project, where we try to, let's say, teach you a little bit something on the room acoustics and oralization for hopefully sound professionals sometime in the future in, let's say, an innovative way. But knowing who my audience is, I decided this lecture will be about theoretical concepts of different sound systems that we use in modern production and in something more like spatial audio. So no mathematics, no nothing complicated. This is the idea. I want you to just understand some basic concepts, what lies behind and how these systems actually work. So I think I can skip this because we had it last time. Okay, so today we'll have the final two lectures. This one should end at 1 p.m. and then we have a demonstration, some practical demonstrations in the fifth lecture, which will use some basic forms of spatial audio. As for this lecture, the first thing I will address is how we go about either creating or recreating a sound environment using anything from mono to some more complicated systems, and then we'll talk about a little bit about each of them. For some you already know, some of them you probably haven't heard about, so the idea is to see what is available to you when you try to go about doing something like this. So, how actually do we either create or recreate a sound environment? Well, the basic stuff that you probably all know about, we have done it before, most of us, is live recording. So we have a, let's say, a concert hall, let's say the one we have here, we have a concert inside, we just put some microphones in there, do a recording, and this is, we document that event in this hall at this particular time. So we have a recording of some sort of concert in a concert hall or anything else. It might be a live band somewhere or whatever. If you want to create an environment in some sort of a simulated condition, then we will use synthesis. So let's say you don't have a recording of your band or orchestra, but you have to produce, I don't know, let's say a rock band from scratch. So you make some tracks, you mix it, you master it, and you create a stereo or some other sort of environment completely, let's say from scratch, yeah. So you do basically, you're mixing, you're panning up the sources, left, right, center. So you do it all in your studio and your control room. The third option would be to do some measurements and use a process called convolution. I think it will be shown in the later lecture. Basically, you go into a room, make acoustic measurements. The most simple one you saw last time. Well, not only, but you use one microphone and one source, and you obtain something we call the impulse response of a room. So let's say I do this, you heard something, some response from the room, and believe it or not, in that impulse response, every information about the room is actually contained. So you have everything you need, and depending on how you actually measure it, whether it's just one microphone or some other more complex technique, you will have some information you can actually work with later. And what we do is we use some sort of dry sound, anything. We convolve it with that impulse response, and when you listen to it, it sounds like as if you were listening to it in that room. This is the idea. And the fourth way, that is usually the most flexible one, is that you use a room, you take a room, draw a 3D model of it, and do some acoustic simulations inside, and by that you can obtain an impulse response in any point in the audience area you choose. You can place the source anywhere you want, you can place more sources, more receiving points, and for each of those combinations you can make a separate impulse response. As you heard last time, if you move like this and the source stays where it is, the impulse response is similar but not exactly the same as it was here. So for any point in space you can obtain an impulse response that is a little bit different than the one before. Again, what we do to actually produce some sound of it, you use these calculated impulse responses and then again convolve them with some dry sound, and then you actually have a feeling that you are listening the sound as it would be in the room. And the greatest benefit is actually that the room might not exist yet. So this we do in the design stage. So we can throw up something and say, aha, if we do some sort of acoustic treatment, the room will probably sound something like that, if the source is there and the receiver is here. So all these things we can do with many different systems, and the simplest, the oldest one is actually mono. So what this is? What is this actually? We use one channel for recording. You record your instrument of any kind with a single microphone, but you use only one loudspeaker for reproduction. That's it. As you can imagine, 100 years ago or more, when this was invented, this was the only thing that actually could do. There was no digital technology, no complex signal processing or anything, so this was the simplest way to actually convey information to people. So if you ask yourself, is there any perception of 3D space? Not really. If I play anything from here, it will come exactly from here. So you will not know. I mean, you will hear some sort of, let's say, reverberation from that recording that I play, but it all comes from the same place. So perception of space is actually almost non-existent. But do we use this? Of course we do. We record our microphones, our instruments, and we use those recordings, those mono tracks as we call them, in production to compile something that is actually not mono. We never mix for mono, hopefully. What we do mix is stereo, of course, which is next. So stereo is already a big jump compared to this. So, but the simplicity of this is actually, if you want to record something, you only need the microphone, one of them. So if you use an omnidirectional one that captures everything from everywhere equally, then you capture everything, your instrument, your space, maybe your audience. If you use a directional one, you know, we have figure of eights, we have cardioids, stuff like that. Then certain directions are favored, hopefully the one that points to your instrument, at the expense of others that you don't want into your recording, some bubble gum, something like that from the audience, and you can use that. What's the actually hard fact here? When you record or measure something using only one microphone, you will record, of course, everything in the room, or most of it, but you will have no way of knowing where these sources actually are. So this information you cannot capture with any kind of mono recording. If you mix for mono masters, to be listened only on one loudspeaker, everything comes from the same place. So again, everything is here or there. And actually the sound of, the impression of space simply does not exist. So the next step was to use two loudspeakers instead of one, and this is the well-known stereo. We use this format up to this day. So this is simply an extension of mono in the sense that we now use two channels for recording, the well-known stereo recording techniques. I will say something about it a little bit later. And of course, two channels left and right, let's say these two, for reproducing our material. So, in comparison with mono, you know, of course, from countless listening that you have done in your lives, that the perception of space is greatly improved compared to the mono recording. You have two channels, whether you listen to them on loudspeakers or headphones, you have a much better perception of space, although it's still actually limited, because if you use loudspeakers, your stereo image is between them. You get nothing from the sides, from above, from behind, and that's it. So you're limited to your stereo base. What we do here, of course, we have two channels, so it requires two microphones, both for recording or measurement. Normally, actually, in cases of measuring something with two microphones in space, maybe impulse response is not that common, but you record some sonic material or orchestra, even a single instrument using a stereo technique, that's quite common. Some of you might know, we had it last year and we have also this year for younger colleagues, that we use two concepts here. So when we try to play with stereophony, we either use intensity stereophony. This relies on the level difference you get with two microphones, which then translates to level difference on the loudspeakers, and then you say, aha, my hearing will produce a phantom source, which will be, let's say, somewhere between the loudspeakers, or in extreme cases, in the loudspeakers themselves. Or we use the time of arrival stereophony, so it relies that you have two microphones, and the time of arrival of that sound is a little bit different for both of them. And your hearing also reconstructs this when you listen to it as the source that's not in the middle, but shifted, let's say, to the left or to the right, so somewhere in the stereo image. This is as far as recording goes, but in the synthesis part, so when you decide to pan your sources from scratch, you will probably not use this time of arrival difference, but we use panning. Level panning in the sense that you will send your mono track into both channels of your master, but depending on where your pan switch is, or regulator, you will apply a little bit more level to one of the loudspeakers, and when you listen to that, your source will run to the right or maybe to the left if the left loudspeaker was actually louder. So how does this look? If these are loudspeaker feeds, I is your source, you apply some gain on both of them. If A is greater than B, left will be louder, and you will perceive the source somewhere to the left, or vice versa. The requirements set on this panning is that your source should be more or less equally loud wherever you decide to put it. So there are techniques to overcome this problem when you reach the center. If you have constant loudness all the time, then the center will rise up a little bit and be louder. So what we do is those gains, when you cross the center, should fall to the opposite side. So right gain goes like this and then falls to the left, and left gain falls to the right. So when combined together, the source appears to be more or less equally loud, whether it's here, 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 or there. Again, when you record something, or in rare cases measure it, you will capture everything, all your sonic content, and only the basic information of where the source actually is. Center, left, right, but all confined within this stereo image. So no height, no backside, no behind you, no up or down. So all of this is actually pretty limited. And as a convention, what we do is, we should do it actually, because most of the standards are actually done for this, is if you listen to it, you will listen to two loudspeakers which are plus or minus 30 degrees to your left and to your right. So they form a stereo base, and in the third vertex of this equilateral triangle are you. So this is actually standard. Yeah. Can we listen over headphones? Of course we can. Most people do these days, but the listening experience is actually a little bit different than what you hear on loudspeakers, which is why we had this in our classes, if you use headphones to mix your, let's say, project, when you listen to it on loudspeakers, it sounds a little bit different. Why this happens? Because with headphones you have perfectly separated left and right. Your left ear hears only the left channel, your right ear hears only the right one. But when you listen to loudspeakers, which is actually how you should do it, then you listen to both of these loudspeakers, both of your ears. So that's why the experience is a little bit different. And this is a concept that we will actually talk about a little bit later, and just remember it for a while. So, as for recording, actually we use a number of these stereo recording techniques, and most of them are rather straightforward. So you have a left and right microphone, you record, of course, left and right channel, and when reproducing, you put the left channel on the left loudspeaker, the right on the right, quite straightforward, and you get your stereo image. How is it created? Well, the human hearing system is actually responsible for that. If it worked a little bit differently, you will be able to hear two distinct loudspeakers. Fortunately, you do not, so the experience is actually much nicer than it could be if the human hearing system worked a bit differently. But your human hearing system creates what we call phantom sources. So you have two real loudspeakers, but you hear a source here, which doesn't exist, here, there. So you get your stereo image of actually non-existent sources. They don't exist in real life, but they're created by the two loudspeakers and you. This is the idea. As for the types of these recording techniques, there is something we call coincident stereo pair. So we use intensity stereophony, directional mics, positioned at hopefully the same point in space or very, very close to each other. We have a space stereo pair that relies on the time of arrival. This utilizes intensity. This utilizes time of arrival. So if you have a source there, with microphones here, the sound will arrive here a little bit earlier than there. And we record that difference and listen to it. Our ears and brain say, aha, it should be somewhere on the left. Your left, my right. That's it. We have a near coincident stereo pair which combines both of these principles, and we have a stereo pair with a baffle, physical baffle between, which is actually the closest thing you have to human hearing other than the dummy head, which actually is an artificial human, let's say. So, to start a little bit, this is actually a repetition for most of you, but when you have coincident stereo pairs, we actually have some sort of directional microphones. As you can see, we have two cardioids here. There are the two figure of eights. So this is an example of such technique, XY and boom line. And since the microphones are actually at the same point in space, we cannot talk about the difference in time because the sound arrives at both of them at the precise exact moment. So what we have to rely on that these two microphones will record some sound from some source with different level. This is pure intensity stereophony. The completely other thing is the space stereo pairs. So we have two microphones spaced apart, usually by at least 30 centimeters or more. It can go a lot. The distance can be greater, of course. And what we use here, usually, we use omnidirectional microphones because, well, most of the time this is for high quality recordings which are made usually in studios, so there is no distractions in terms of bad acoustics or, let's say, I don't know, audience or something like that. If there is something like that, if you record something live, you could always use, let's say, cardioids, but then you should point them towards the source to reject anything that comes from behind, whatever that might be. So the basic technique would be the AV, so-called. And for large stuff, let's say symphony orchestras, you can also use something called the Deca tree. So you have the basic AV, but you have a third microphone in front to address the fact that if you space the microphones too far apart and you can have a clear center, then something blurry or nothing, and then something coming from the far left or far right. So part of it is missing, and that's really why we added a third microphone to fill this hole, so to say. But, as I said, this is only the time of arrival stereophony, so if there is any difference in level, it's so small that it's actually not important here. So the whole thing relies on the difference of the arrival times from the source to the both microphones. A combination of these principles, I mean the techniques that use both of them, is the so-called near coincident stereo pair. So you see we have two directional microphones, So we obviously are counting on capturing some level difference from a source that's somewhere there, not necessarily in front of you. So as a rule, these microphones are cardioids, so we use always those. But we also set them at a fixed distance. So there is some small distance between them, and the distance is meant to emulate the separation between your ears. So 17 centimeters is realistic, 30 not so much, more or less. And examples are usually those developed by the big TV houses, including ORTF that we use actually a lot. NOS, RAI also has a technique of its own, but the difference is actually how far are these microphones apart and what the angle is between them. This is the only difference, but the principle is always the same for every technique. But for those of you who have taken my course about audio technique in the electroacoustics, there is one very specific stereo recording technique which does not actually conform to what we just heard about every other. And this is the mid-side stereo technique. So what we actually do, we have the mid microphone, which is, as a rule, it should be the omnidirectional one. So basically it captures everything. So no matter where sound is coming from, it will capture it with the same level, ideally. So you have the complete recording. You could use it as a mono recording quite nicely, but you have no idea where your sources actually are. So this is not stereo just yet. To be able to create a stereo image out of that, you will need the so-called side microphone. So if your source is here, your side microphone, as you can see, is the figure of 8. I think we actually did something with that. And it's placed perpendicular to the direction of your source. So if the source is here, by definition, your figure of 8 points to the left. If you remember, the figure of 8 microphone actually has two lobes, the positive and the negative one. So if the figure of 8 is here, I clap from this side, my membrane will do that. So I will record a positive impulse. But if I do the same from here, the membrane will do that in opposite direction, and I'll record the same pulse but negative. And this is crucial for actually recording the part that's missing, to be able to place my sources where they should be in that stereo image. So how do we do that? Well, when I said that this technique actually is different from all the others, we cannot just play one channel here and one there and expect the stereo image. This doesn't actually work that way. But actually the stereo image, this is actually underscored because, underlined, because this is an important concept. So you have the M channel recorded with an omnidirectional mic, and the S channel will be the figure of 8. And this, your stereo image is somehow encoded in that information. It's not something you can directly reproduce. So to reproduce this, if you remember this, we actually need to do something with those two signals to make we call them feeds, our signals, final signals for the left and right, to be able to hear the stereo image. So this information needs to be decoded from those two. And how we do this? How do we do this? Well, simply, if we had the stereo setup MS as shown earlier, we simply add those two together for the left channel and subtract S from M from the right channel. And then we can play that and get our stereo image as it was intended. This encoding and decoding will appear later, so please remember this. This is an important part of another much more complex technique. So the important things to remember here is that our final feeds for our loudspeakers are created, you see, from both of those we had before. We could use the term all of those, but we have only two, so let's say both for now. So this is important from something more complex that we will have later. As an extension of stereo sound, I don't know how much people actually use this stuff at home. Some do, actually. But then it's, at the time, those 5.1 surround home cinemas were very popular, but I don't know how much people actually use it. But here is something just like that. So this is a 5, actually 0 because there is no subwoofer here, but never mind. So this is actually an extension of what we call a classic stereo to some more space around you, still without height actually, at this point. So you have these loudspeakers that will be somewhere to your, let's say, to your sides, and your image will be a little bit wider than it was with classic stereo. Over time, these formats have evolved into, I don't know, let's say many different configurations. So when this horizontal listening, so horizontal plane around you was resolved, then they started to add some height coverage. So loudspeakers, let's say on the ceiling, that would really give you an impression of, let's say, more or less 3D sound. So if you, let's say, open a page about, I didn't write it here because I actually don't know how much I can advertise certain brands or so, but Dolby, let's say Atmos, you will find many different configurations depending on the number of loudspeakers around in the horizontal plane, depending on how many there are in the on the ceiling for height information, depending on how many subwoofers they actually use. Most of them actually do, because it's much easier to use, let's say, 1 or 2 subwoofers than to build all these loudspeakers as full range down to, I don't know, 40 or 30 hertz. So use those satellites as small loudspeakers, and you use 1 or 2 or more large subwoofers, which are actually, it doesn't really matter where in the room they are, because low frequencies you cannot, if you listen to any kind of system like that, you cannot localize it where it's coming from, so it doesn't really matter. So if you see something like this, 5.1, 7.1, something like that, what does it mean? 5, it means just that you have 5 loudspeakers in the horizontal plane, and 1 that you have 1 subwoofer to cover the low frequency, the LF feature, and the low frequency effect. If you see a designation such as this one, the third number means that you have some height information. So you have some either loudspeakers on the ceiling, physical ones, but there is also a technology available that actually uses not physical loudspeakers on the ceiling, but it uses sound produced from speakers that are actually not on the ceiling, but somewhere else in the room, but it uses reflections from the ceiling to give you this height information. So these loudspeakers can be real, but they can also be virtual in the sense that there is no real source on the ceiling. So you have a loudspeaker there, it's used as a, let's say, front, but it also can, let's say, emit something to the ceiling to reflect, add the list position, and provide as if something was actually coming from the ceiling, some information. So this is actually widely used. And now we come to the interesting stuff, I would say. There is a system, I'm not sure how much it's actually popular, whether it's in the domain of research or consumer. I think not so much in the consumer domain, but anyway. And this is called the VBAP, or the vector-based amplitude panning. So what is this? Well, as a start, let's start with something simple. This is simply, you have your 2 stereo loudspeakers, and you extend with the third one to get some height information. This is very simple. So you still have your stereo image between those 2, but if you include the third loudspeaker, you form a little triangle. So basically, in theory at least, you could place the source anywhere within that triangle. So what are the possible cases? If your source is here, or here, or here, then only that loudspeaker will be actually reproducing. These two, the other two will stay silent. Why? Because they are not actually needed. The same as with stereo, with two loudspeakers. If you want the sound to come to you and for you to perceive directly from here, the other guy can stay silent. So this one is the only one that needs to actually produce sound. If you want the loudspeaker, the source, the virtual source, to be somewhere on those edges, let's say you want it here, then these two will run, this one will not. This is also classic stereo. Or here. These two will be active, this one will be not. But if you want your source to be somewhere from inside, let's say here, then all three will work together to create that the impression that the sound is actually coming from here. So how do we do this? So we have, well, not left and right anymore, but the three loudspeakers. We have our source I, which is here, and we have to figure out these gains, A, B, and C, how much gain we will put on each loudspeaker, for us to appear that the source is coming from, let's say, here, or here, or here, or here, or I don't know, here, or any case will work. So, okay, you will say, but this is not 3D. That's right, it's not. Not yet, anyway. How do we make it 3D? We make more triangles, basically. So we make some sort of sphere-like configuration of loudspeakers, and then you, okay, this is a rainforest of lines and everything, so you can maybe not see it clearly, but let's say here. You basically form elementary triangles like the one we saw before. So if we want our source to appear here, so these three loudspeakers will be active. The others will not. The others will stay silent. Or I don't know, if you want the source to come from, let's say, here, those three will be active. The others will not. And this is basically it. This is how it's done. So the basic idea is to figure out which three loudspeakers will be actually active if you place a source somewhere. And what the algorithm actually does, it will calculate all the gains for all the loudspeakers you have, but if you want to reproduce something from this direction, only actually these three will be positive numbers, the others will not. So this is how you say, if I have a triangle with three positive numbers, A, B, and C, they're all greater than 0, then this is something real, and all the others will not work anyway. So this is how it actually runs. Okay, this is maybe a little bit too much for this level, but anyway, you can do 3D with VBAP, but remember, it is like just an extension of classic stereo in 3D. So you divide your space with loudspeakers into these elementary triangles. If I want it here, activate this tree. If I want it there, activate that tree, and that's it. So this is how the system actually works in reality. And now we come to something that's very close to, I mean not close, but it's something that actually defines us as human beings, but also I would say any animal that uses 2 ears to listen. So it's not reserved for us humans, but for any animal that uses this kind of listening system to, to localize the sources around it. Some 1,000 years ago, we were actually hunted by, I don't know, predators. It was important to know very much in advance where they are, so you can do the fight or flight routine. So either run away if you can or fight it. Okay, I'm not saying that today is different. People often forget that because now you have cars, motorcycles, anything that can strike you from behind it, and you will never know it. But the odd thing is that people choose to isolate themselves by wearing headphones, and you are in traffic. So this is not very, maybe the world has changed a little bit, but they're not hunted by predators, but there are other dangers to lurk from behind. So, to get back to this, basically this 2-ear system that we use is called binaural hearing. Bin as in 2, oral as in actually listening. So there are two basic mechanisms. If you remember what we used in the stereophony, you will say, but this is actually quite similar to that. So what do we actually use? We use something called the interaural level difference. And what is this? Basically, the level difference in sound that arises at your two ears. If you look at this guy here, if the source is there, you can be sure that the level on the left here will be a little bit higher than the level on the right here. Why? Well, it's a little bit further away. This actually doesn't make much of a difference, but the head acts as a shadow, so it attenuates sound a little bit. And the other mechanism is the interaural time difference. So the difference in time the sound needs to reach your ears. So if the source is here, it will reach your left ear a little bit sooner, earlier than the right ear. So there will be a time difference. If you look at these charts, they depict exactly that. So the red signal arrives, you see first, it's a little bit louder. The right, actually sound, not a signal, arrives to your right ear a little bit later, and it's a little bit weaker. From those two things, they give you the basic you need to actually localize the source, at least in the horizontal plane, more or less, from the part that could be or should be the most important. But is this actually enough to describe our localization, the way we localize sound? No, it's not. It's a start, but it's not enough. Why? Because actually, when you consider the localization in terms of those two numbers, actually, you can get very similar numbers for different directions. There is an example. If you are listening to me, or I'm listening to you, and you're right in front of me, the time difference is 0. The level difference is 0, too. Because if you're in front of me, like you are, okay, I'm talking now. But if I go up directly above you, the time difference is still 0, and the level difference is still 0. But you will know that I'm above you, not in front of you, or behind. It's the same thing. So there must be something else, because these numbers will be the same for all three directions. In front, up, and back, and down, for that matter. Or anywhere on that, let's say, plane. So there must be something else. So, how can we actually distinguish between those positions? Well, I wouldn't say solution, but this is a fact. So, for every direction, the sound changes a little bit differently. Why? Because your head is here, the ears are here, your even body is here. So these little changes, they can be actually very, very small. But from years of listening, your brain will learn, if the sound is changed exactly that way, then the source must be in front of me, or up, or back, or I don't know, to the left, to the right. So we can describe this with something we call the head-related transfer functions. So this is basically a characteristic that we can measure. Or, I think, maybe even the better parameter would be the head-related impulse response. Because this impulse response contains, as you will see later, all this information. So the ILD, ITD, and all these small changes that actually affect and help you to know the exact direction of the source. So maybe those two are just not enough, those two, let's say, numbers. You have to have something else. So the point is that actually sound changes before it reaches your ears in a very specific way, depending on where it's coming from. From the front, from above, from the side, or any actual direction in between. So you can measure your HRTF from here, and it will be already different if you measure it for that direction, or that, or that, or that. So what you should do is actually measure a lot of them, all around you. And this is actually done in what we call resolutions, so every maybe 5 degrees, 3 degrees. It depends on how much time you have and how complex the method is. It's usually very complex, and people just don't have the time or the patience to stand still and wait for the measurement to be finished. In the early days, it took 8 hours. You can imagine. You can stand like that for 8 hours. So over time, it was reduced to, let's say, 3 minutes, 5 minutes, 10 minutes. Okay, this we can do. Again, the fact, it's not an advantage or disadvantage, but the pure cold fact is that these impulse responses, or transfer functions, as you would call it, are quite unique for every person. But why is this? We are all different. So no two people are actually the same. From the shape of your earlobe, from the size of your head, nose, I don't know, weight of the shoulders, anything. So every person changes these sounds a little bit differently. So if you would like to have a unique binaural listening experience, you would need to actually get it measured for yourself. And this would be the best. This way you would get what we call a set of individual head-related impulse responses. Just yours or mine. And when you use this to create your binaural sound environment, you get the best possible listening experience because they are yours. They are what you are used to. But actually, for reasons I already stated, this would be quite a complex thing to actually measure. It would take some time. So what we use instead, we use generic ones. And as measured on something that serves as something average for all of us. And what's that? What you've seen last time, a dummy head. How good the representation of an average human this can be debated, but we actually use this in oral simulations to say, okay, this will be a compromise, meaning that it will not be ideal for anyone, but it will be, let's say, good enough. So you'll be able to distinguish your image, at least from left to right, and get some sort of spatial impression. It won't be perfect, but it will serve good enough. So, as you can see on this picture, this is actually an example of these impulse responses, head-related. So you can see that when you look at the time and the level, the left one obviously is a little bit stronger and it came a little bit earlier. So whatever this was, and the right, so whatever this was, it was measured for source somewhere on the left, general. It could be there, you don't know. So from that you can get actually these head-related transfer functions, and you can see by frequency how the sound is actually changed for your left and right ear for the source in that specific direction. If it was here, this would be a little bit different. If it was there, again different. So it's very specific for every person and for every direction. This is why we measure a whole set, not just one. Okay. When we listen binaurally, but also stereo actually, this is not this is not limited to binaural systems. There is something that we call static binaural system. What does that mean? So, if you listen to a binaural recording of something, let's say a source that was in front of you, in front of the actually dummy head that did the recording, and if you turn in a static system, of course the source will follow you and still be in front of you. Is this realistic? No, of course not. You expect if you turn your head to the right to hear me from your left, and not by some magic that I appear there. So this is not realistic. But actually, when you listen to any kind of music or stereo recording, this is the same. It's static. I mean, if you turn your head, your stereo image, okay, it's in your head from left to right here, but okay. But it follows you. But is this so in real life? Not really. So the source would have to stay, I mean, you should perceive it at the same place, no matter where your head is. And this is something that the static system cannot do. So in the static system, your binaural image follows you around as you turn your head when you're listening. So what do we do then? We use something called dynamic binaural systems. So if you have a listener, let's say he perceives the source from the front, when he turns right, as you could do, I mean, turn your head right, but source should stay at the same place. So this is exactly what we want. When you turn your head to the right towards the control room, you should hear me from your left, not in front anymore. For that, I mean, this is the real thing actually. Of course, if you have a source somewhere there, now it's in front of me, to my right, above me, more or less, behind me. So this is what I want to have. So, how do we achieve this? Well, actually, to know what to do in our, let's say, synthesis or reproduction, we would have to know how much we turned our heads, actually. So to know this, we have to use something called head tracking. This is by definition. So you have to know where your head is oriented and how much you actually move it. So for this we use head trackers. Let's give you an example. Let's say this is some sort of synthesized environment and you want your source to be here. Okay, so when you're facing it, it's right in front of you, but when you turn your head, you should hear it from your left, of course. So you would have to know, I turned my head 90 degrees, so my source should not be there. But do we do this in one jump? No, not really. So we would have to do it in many jumps. So fill some spots in between. So for every time we will use a specific pair of these HRTFs. This one is from the front. This pair puts the source to your left, but also something in between. So to make this transition smooth, as it would be in real life. So not just jump from here to here, because the source is immediately to your left. This is not how it works. So you'll synthesize some in-between positions, let's say every 10 degrees, every 5 degrees, however your system is capable of, let's say, swallowing in the processing sense. Maybe even every 1 degree to be as smooth as possible. So this is actually what we use to create the impression that our source is stable in the outside world. So it doesn't follow us around when we move our heads. So it stays there. So this is the real thing, actually. So, to go back to how do we, let's say, either create or recreate a sound environment. So we can always do recording. We take one of these dummy heads. Actually, the very distinction of it, the defining characteristics of a dummy head is that it has 2 microphones where your eardrums should be, in some sort of ears that are, well, not really well defined, but average enough to do the job. So we make a recording, we put it in a specific place in the audience, let's say, and record whatever needs to be recorded, let's say, an orchestra in the room. What you also can do, you can use a live person. There are some, there are equipment in very small in-ear microphones that you put literally close to your eardrums, and you play the role of the dummy head. Of course, if you can maintain still enough for long enough to play the role, and not, let's say, move or breathe too loud or whatever. But it can be actually done. What else can we do? We can measure something called the binaural impulse response of the room. So we don't use just one microphone to get an ordinary impulse response, but we use a dummy head or a pair of microphones for that matter. So why is this better? I mean, what new information does this bring? Basically, we know that for every direction of arrival to our ears, or to the ears, let's say, of the dummy head, the sound changes a little bit differently. So if you use that to record the room, this will stay recorded. So basically, you will know the direction of any, let's say, reflection of sound. You can say, any reflection of sound is a sound source. So you'll be able to record not only that these directions have arrived, but where they arrived from. And this is much more information because you have a spatial information inside. With a single microphone, you cannot do it. It collects everything, but it doesn't know where they come from. Because the dummy head or live human actually know, can tell where the sound comes from. This stays recorded. So you can record the room, the impulse response of that room through the dummy head. And then you get the directional information. So how would you actually use this? Well, when you record it, you can say, okay, we can convolve this with a dry signal, anything, one instrument, two, whatever, and the reproduced result then sounds as if you were listening to it in that hall, if it stayed on that position in the hall, particular one where the source was, and you were seated in the audience where the dummy head was back then, when you measured it. So you can make many actual measurements, not just one. The front row, I don't know, somewhere to the side, way in the back, and you can make many impulse responses for the, let's say, for the richer description of what that room is. When it comes to production, or let's say binaural synthesis, on top of everything that you would normally use actually in mixing or mastering, you can use something called binaural panning. So you can place your source anywhere around you. So how would you do that? Well, you take your monotrack, and let's say you want to place it there. You say, I need a specific pair of those HFTFs, left and right. And when I convolve it with my dry signal, when I listen to it, it will appear as if the source was actually right there. If I want it here, a different pair. Here, a different. Here, again, a different one. And, of course, we can always do room acoustic simulations, and our programs normally produce exactly that. So these binaural impulse responses. Why? Because no matter if you measure them with a dummy head or produce it through simulations, you can again convolve it with any sort of dry signal, and the end result, if you listen to it, will sound exactly as if you were there at the time. I mean, that of course depends on how good your simulation actually is, how detailed and everything, but you can actually do it, and the biggest advantage is that you can do it in advance. You can do it for virtually any position in the room that you choose, 1, 2, 10, 100. So it's very, very flexible. What do we do about listening? Well, by definition, binaural signal is meant to be listened over headphones. So why is this? Because this imitates real life. So when you listen to your source, you get perfectly separated left and right ear. So if you want to listen to the binaural signal, you would need to also achieve that. So you would need left channel only to your left ear, right channel only to your right. And this is something you can achieve with headphones. Remember what we talked about stereo. So stereo was not meant to be listened that way originally, so it sounds a bit different on headphones than on loudspeakers, but binaural is actually. So you should be able to bring your left information from the left channel only to your left ear and the right only to your right. Does this mean we can listen to it? I mean, does this mean that we cannot use loudspeakers? No, we can use them. But let's leave it for the next period. Take 10. I think it's a little bit overwhelming. Okay, so this will be the topic for the after break. Take 10. Okay, welcome back to the second part. So, where we stopped, actually we said that for reproducing binaural signals, we should normally use headphones because we need perfect separation between left and right ear. And we should not allow any what we call crosstalk. So what does crosstalk mean? It means that a signal normally meant for one ear is heard by another. And this is what you would normally actually get by listening to loudspeakers. So here is actually what we are dealing with. So we can actually use these two loudspeakers in some sort of formation. It does not have to be sterile. They can be literally spaced, I mean, set almost next to each other for this to work. But what we need to achieve is this. So if you listen to, let's say we forget about the right loudspeaker for now. If you listen to left loudspeaker, it will of course be heard by both of your ears. And the same is for the right. But what do we need to achieve? We want the left loudspeaker to be heard only by the left ear, and right speaker to be heard only by the right ear. So these paths, left, left, right, right, we want. But these guys here, the LR and the RL, this is the paths that are heard by the opposite ear. So this is what you hear with the right ear, if played on the left loudspeaker, and vice versa. So this is something we do not want. So this is crosstalk, and we need to somehow get rid of this if we want a clear situation that you actually hear, let's say, left speaker with only left ear and right speaker with only the right one. This is the only way for you to perceive these binaural recordings the way they were meant to. So, how do we go about solving this problem? The simplest, actually, crosstalk system consists, as I just displayed, of two loudspeakers in front of you. There are more complex ones, of course, then some parameters actually change it, the calculations become more complex and everything, but let's start. I mean, I want to show you the basic principle of what we call crosstalk cancellation issue. So let's say here you see left and right loudspeakers, what they produce, and here we have left and right ear, what they actually hear. So let's say that we want to have the left loudspeaker produce only a single click, only a single pulse. It can actually be any kind of audio signal, continuous, intermittent, interrupted, but for the sake of simplicity, I will just show you what happens for a single pulse. It's the easiest to draw, actually, that's why. So what happens? The left one produces only a single pulse, this one, and in the first step, these numbers actually depict the sequence in which this unfolds. So it arrives at your left ear. Okay, we want that. This is actually the thing we want. But the problem is that you will hear that click with your right ear as well. You see, it will come a little bit later in time, of course, it's on the other side. It will be a little bit weaker than here, because your head acts as a shadow. This is what we learned from the binaural listening. So you would say, now we have a problem. What to do with that? So we want this pulse heard only on the left ear, but you of course hear it on the right. So we need to cancel it somehow. So how do we do this? We say, we will let the right loudspeaker emit a counter pulse. You see, the same as here, but reverse polarity. So this one does that, it arrives here, and when it's summed up with this annoying one, let's say, it cancels each other out. So you will say, so okay, we solved the problem. But did we really? No. Why? Because whatever this guy emits arrives here also, a little bit later in time and a little bit weaker. And what do we do now? Again, we use this one to cancel that one. And we actually do cancel it. It's heard here. We use this one to cancel that one. It's heard there. We use this one, actually there, yeah. We use this one to cancel that one. It also arrives here. And we use this one to cancel that one. And at this point, what arrives here is so weak that this process can actually stop. Because you see, every time, in every iteration, the amplitude gets a little bit lower. Why? Because the sound travels from this side to here. Arrives weaker, we cancel it. This arrives weaker, we cancel it. And this can go on for, I don't know, It depends actually on the system, how many of these will be. But this is actually the basic how we do this. But remember, we had to do all this just to play a single pulse on the corresponding ear. So you have to produce all this to get this result. So it's not as you would say, I mean, it's not really complicated at this point, but it's a lot of work, additional extra work for the loudspeakers, for the whole system. Remember, this is only the 1/2, because we only have left loudspeaker play some content of the left ear. You can also do the same for here, and you will get, actually what's missing here you will get down there. So if you actually look at this, this is what you would call half actually of the impulse response of your loudspeakers. I mean, your, not loudspeakers, but filters you need to make this work. This is what you need to do to play left-left. We could always draw the same thing for the right loudspeaker and right ear. It's the same thing. What are actually the most important parameters here? There are some plugins you can find even on the internet, actually quite old ones, which will do the work quite decently. And you will be probably asked to set this, what they call delta T. So the difference between sound arriving here and there, the time difference. What will this depend on? Basically, how far you're apart from the loudspeakers and how far they are actually apart. They can be wider apart, they can be set almost next to each other, you can be closer, you can be farther, so for every such configuration, it will actually ask for a, let's say, specific time difference, delta T. This will be in the range of some parts of milliseconds, so it's very, very small. Also, you will probably be asked to input something called the attenuation rate. So what is this? This is simply how much the next pulse is weaker than the previous one. So if you set this thing to 3 dB, you start with 0, so the second one will be 3 dB smaller, so -3. The third one will be 3 dB smaller than that one, so -6, -9, or so. You can also be asked to estimate at least the number of the cancellation components. Of course, as a user, you will not be able to do this just like that. You can, let's say, play around with it and you will get some, well, good or less good results, but you can do it, let's say, by ear. After half a day of playing, you will know for your configuration what to expect. This is actually the most basic way how these systems work. You can not limit yourself to only 2 loudspeakers. In research you will find, even in implemented listening, let's say, labs, you will find some implemented systems which use more than 2 loudspeakers, 4, maybe even 6. But to understand how this works, I think this is for now quite enough. Here you can also see the term static cross cancellation. What does that mean? Well, basically it means if you put your system somewhere in the room, you should maintain very fixed position, so not move around, not turn, not anything. So you need to be at a fixed point in space, and then the system can use the filters to produce the loudspeaker feeds that are constant. It's always the same. Why? Because the situation is completely static. The loudspeakers are here, you are there, or vice versa, and you don't need to change anything. But if you want to be able to move in space and still have the loudspeakers where they are, and still have the impression that you listen to the binaural signal as it should be heard, then actually the system would have to know the position of your head and its orientation. So whether you move, front, back, left, right, or wherever, whether you turn your head or not, and then use this information to adapt these filters, to change these parameters, so that this impression I mean, this, well, not an impression, it's actually a physical fact that you are able to cancel the signals from loudspeakers on the opposite ears, that it actually works properly. So if you want to move around, then you need head tracking. How do you go about head tracking? Well, there are different devices available. Professor Jambršić had a project just recently where actually he examined the ability even of cell phones to do the head tracking, and I can tell you they do it quite well actually, because they had all the necessary sensors and signal processing already inside. Otherwise, if you take your cell phone without these sensors, you never know how it's pointed in space. If you, for example, open Google Maps, you will see that your cell phone somehow knows which side of the world it's pointing at. So this is thanks to those sensors, and the same ones can be actually used to track your position in space. If you tape it on your forehead, or I don't know, make some kind of concoction to fasten it to your head, you can actually do it. And this can be done that way. But actually there are dedicated devices that will do it for you. It doesn't have to be just cell phone. But this is actually how it works, so in most simple terms. And now we come to the penultimate chapter, a very actually interesting technique, not quite trivial, I would say, because it requires, if nothing else, a considerable amount of equipment. So it's more maybe research-based, but you can also find it already in gaming and even on YouTube 360 and stuff like that. And this is called ambisonics. So what is actually this? This is not as new as you will think. This is 50 years old, but at the time there was no digital anything. It was in its infancy, and there was no way to actually implement it in real life. Only the most basic stuff could be actually implemented. But now in the 21st century, our computing capabilities and everything have grown, well, maybe even more than anyone expected. So these systems are now very easy to implement. Something which was impossible when it was invented. So what is the core of the system? It's actually a way to describe a sound field all around you. So let's say you want to describe something on a sphere that's all around you in 3D from a single point, from the point of the microphone. So if you say, I think I heard that somewhere. So where did I hear that? Where the coincidence stereo techniques also. They use one point in space, ideally at least. So this is something that we might even begin with when we describe ambisonics. But not just any technique, but the MS stereo. If you remember what MS stereo is, it's the most primitive version of ambisonics possible. So what did we have there? As you remember, we had an M channel, an omnidirectional mic. It records everything from everywhere, but no direction. So you collect all sound, but you don't know where it's coming from. To know where it's coming from, you add an S channel. Why is it in two colors? Just to say, everything from the left is positive, everything from the right is negative. So it has two lobes. These are actually in 3D. So any directional characteristic from the microphone you can envision in 3D, not in 2D. In 2D, this would be a circle. Here it's a sphere. Here it will be just a number 8, and this is a 3D figure of 8, of course. So why two colors? Well, it's pointing to the left side gives a positive signal. If something comes from the right, you will get a negative signal. This is the most basic way to record this information, that some source is to the left or to the right. But as you can remember, you cannot directly reproduce this without doing something else. When you record this, you have this information about direction somehow encoded. This is a term that is widely used in ambisonics. This information is encoded in these two signals. So to reproduce it to your two loudspeakers, you need to decode it. So you remember how we did it. To get the left channel, we simply added up this and this, M plus S. to get the right one, we subtracted S from M, so M minus S. So this was decoding for MS stereo. The most simple one you can possibly imagine. And now comes the fun part. Maybe in some circles you'll hear the term double MS. So what is that? Well, we just built on our classic MS, which was Omni and our figure of 8 from left to right, and then add another figure of 8 front to back. So let's say we have a one Omni microphone, and if you can imagine putting them all together close enough, you have two figure of 8s. One covers the left right, and the other covers front back. If you remember the MS, we were just hoping to place the source somewhere in the stereo image to say, this is far left, this is close to the middle, this is maybe here on the right, this is far right. So we had only one dimension from left to right. If you add the second one, you also have the information from front to back. This is the same thing, just turned 90 degrees. Remember, we are still in the horizontal plane, so this is 2D. This is not 3D just yet. And we can record that, and actually some engineers use this. They call it the double MS, which essentially this actually is exactly that. But this is also the first order, the simplest 2D, so two-dimensional ambisonics. So what we have now, we have still the Omni channel, but we don't call it M like in MS stereo, we call it W, this is the convention. We have the X channel, which is the figure of 8 in the front back, and we have the Y channel, which was earlier called S, from left to right. So why is this important? Because if you have information, the information where the source might be from left to right, but also from the front to back, then you can basically place it anywhere in the horizontal plane when you combine these three signals. Let me give you an example of that. Sorry. So imagine this. So you have your Omni, and let's say you have 4 positions of your sources: front, left, back, right. Let's say we are looking from above, for simplicity. So for all these positions, what will your Omni mic give, your W? It will be the same. It will capture exactly the same thing, no matter where your source is. So this gives you actually nothing in terms of where your source is. It just gives us the information what it is. So you capture the sound, but using only that, you actually don't know where it's coming from. But if you know your source is from the front, your X figure of 8 actually faces the front. So it will give a strong positive signal to reflect that. What will the other give? The Y signal, of course. No, it's okay. The X. If the source is at the front, this one should not give anything. So you will know, with this and this, I can place my source directly at the front. If it's the left, this will again give a lot, of course. But this time, the Y signal, which is pointing toward us, that source will give also a positive pulse. You will say, then my source has to be on the left. Moreover, because your X gives nothing, it should not give anything, of course. And the same for the other two positions. If you have some sort of, let's say, more general position, let's say the source is here, then you will get, again, the Omni signal, positive X, positive Y. If it's here, you will get the Omni, always positive. This will be X from back, okay, negative, and the Y still positive. And all around. So with those two, you can place the source anywhere around in the horizontal plane. So this is basic 2D. And this is actually used, you will, if you go to some sort of a, I don't know, recording page where recording engineers assemble to, I don't know, gather, talk, whatever. They will say, I used NS and then matrixed it to my 5.1. It will just mean that he decoded that signal for the 5.1 system. Okay. And finally, this is actually my term triple MS. I didn't hear it anywhere. So what do you do? On top of the two that you already have, figure of eights, you add one more for up and down. So you have one omni and three figure of eights, front, back, left, right, up, down. So what do you do with that? If you know all three, you can say, my source is somewhere in space and I can actually place it. For example, if I know that I have three positive signals from this, so my source must be somewhere in the front because I get positive from that one. It must be somewhere in the left, so somewhere here, because I get positive from this one. And it must be somewhere up, because I get positive from this one. This way I can place my source somewhere in space using one omni and three figure of eights. And this is what they call the first order, so the most basic form of ambisonics in 3D. Because you can place your source actually anywhere around. It will not be very precise or anything. Just imagine you're musicians, most of you, if you had to describe the sound of an instrument with your fundamental, and let's say the first three aliquots, would that be good sounding? Probably not. Because the higher ones are still missing. You would say, maybe it's some sort of violin or viola or whatever, but imagine having only this, only the fundamental. You would not be able to distinguish between instruments at all. This is the same thing, but in terms of space. So with this, you have everything, but no direction. You don't know where they are. If you add that, you have the basic direction of where your sources actually are in space. So what I said, this format, ambisonics, which you can get with one omni and three figure of eights, is the most basic ambisonics format. And in theory, even in practice actually, if you want to play with it, these recordings and measurements can actually be done if you use an omni mic and a three figure of eights. But remember that this is a coincident technique. So these microphones, their capsules, should ideally be very close to each other. Ideally, they should be in the same point in space, which you cannot actually achieve. So, in practice, to avoid having to cram 4 microphones in basically the same point in space, or very, very close to each other, we use something like that. So this is a replacement. If you use this theoretical format, you will get what we call B format ambisonics, from which means we start. So this is the resulting encoded information about the location of your sources in space. This will not get you B format, not directly. Why? Because these actually 4 channels are not figure of eights, they are not omnidirectional, they are placed in some sort of funny manner. Actually, this, if you took what's called a tetrahedron, this is a 3-sided pyramid with all sides the same, and glue the capsules on it, you would get that. So these are actually 4 cardioids in that configuration, very specific spatial one. And this is what will get you the A format, so-called. So this is not, you're not quite finished when you record the raw signal. So you need to get to B format somehow. How do we do this? Actually, at this point, this is actually quite simple. I can show you. You only need to take the raw signals you get from these microphones, raw in the sense that this is exactly what you record, and you have to combine them somehow to get your WXYZ. So something you would get if you recorded with only 3 figure eights. So if for example, this microphone is actually facing you, facing the room, this would be FLU, front left up, literally, front right down, back right up, so behind, and back left down, sorry. So how do you arrive from A, so these raw signals, to B? Well, you simply, you see for the omni channel, you just sum up all of them together, and for the others, you add some of them and subtract some of them. So this conversion is actually quite simple. This is something you will find actually in the manual of this specific microphone. I just put the reference here, but I'm not advertising any specific drive. So, you can use actually something like that to emulate what you would get with an omni mic and 3 figure of 8s. But the best part in this is that you don't have to actually emulate, I mean, you can use this for other things. So you can also emulate, let's say, a stereo pair, or a cardioid mic, or an omnidirectional mic, or anything. So you can take that microphone and say, I want it to, as a result, to have XY technique, let's say. So 2 cardioid at the right angle. So I can do that as well. How do I do that? I do something like that, but take a little bit different amounts. I don't know, I'll take half of that, maybe subtract it or whatever. So some sort of transformation like that one, but I will take different amounts of those signals to get, let's say, my stereo pair. So I can basically emulate just about anything with that. This is the best part of ambisonics. As I said, everything that we heard now is basically the most basic way to place your source somewhere. So it's very, very coarse information, very rough. If you want more detail, I mean, space-wise, you should go to something that we call higher order ambisonics. So if you go back to that, these are first order ambisonic components. So the most basic ones you can have to encode the directional information. If you want something more detailed, you go maybe to second order components. As you can see, they are a little bit more elaborate in space. So they divide the space in more than just, let's say, 1/2. It's not just left positive, right negative. It's a little bit more complex, more elaborate, and if you use them, you will get a little bit better representation of where your source is. If you use first order ambisonics, you'll say, my source is here somewhere. But if you use second, you will add a little bit more detail. So you'll say, it's here maybe. If you use third, you see there even more detailed, you will say, it's here. If you crank it up to 5, 6, 7, you say, okay, it's here, I can point it right there. I can hear every string on that violin. What is actually specific about this? Well, these shapes actually seem quite random, but in fact they're not random. So the shapes of these components, in actuality, these should actually be microphones if you can produce them. You can. So first order microphones are figure of 8s. We have them actually, but these we do not have. So we have to find some other way to get around that problem. So these shapes are not random, not at all. They follow the group, I would say, of functions that we call spherical harmonics. So this is connected to this is the core of the ambisonic system. So if you go back to there we have a basic division: left, right, up, down, front, back. And these guys here divide that space a little bit more in detail, elaborate. So you can record the sound around you with a little bit better idea of where your sources are. I mean, you can pinpoint them. It's more accurate and more precise. So can we directly record these components? No. There is no way, because we don't have microphones and probably never will that produce directly that. But what we can do, just like we did before, you can use some kind of a complex microphone, I mean more complex than what I showed you. And we can record raw signal, we can make some sort of transformation, okay, a little bit more complex than the one I showed you, and obtain ambisonics components as if they were recorded with something like that. We don't have such microphones, but if we can manage to obtain signals that look like if they were recorded with microphones with that directionality, then we arrived again to the B format, but in higher order, not just number one. So what do we use here? You saw some of this on the last lecture if you have been. For example, this is the so-called octomic. It has 8 capsules, so it can record not first but second order ambisonics, so a little bit more detail. This is called the Zilia. It has somewhere inside, I mean, on the surface it has 19 capsules. So in theory it records third order ambisonics. And this is the Eigenmic 64. This is the highlight of what can be used today. So it has, as you can see, 64 microphones. And these are not even directional in any way. These are omnidirectional mics. But when you place them on a sphere, you get what we call an array. And you can do with those signals practically anything you want to get. And this records up to 6th order, I think, or something like that, ambisonics. So very, very detailed recording you can actually get. Yeah. So what I said before, ambisonics in terms of recording offers you high flexibility because you can use any of those mics to emulate not only, let's say, figure of eights or those second and third order components, but you can emulate a stereo pair, something you would use to maybe record a surround signal, or maybe even a single microphone, although that would be maybe a waste of money and technology only for that. But actually, yeah, you can do pretty much whatever you want with it, except you cannot emulate actually spaced pair as a stereo pair, because by definition ambisonics is not that. It's a coincident technique, so you record everything from one point. So you cannot emulate a spaced pair. You could try, but it doesn't work that way. Yeah, and whatever you obtain in this way, you get to this B format. In the basic form, that would be omni and a figure of 8, or 2 or 3 of them. In higher order, you would get all those components that add more detail. And this is the encoded signal. So this is something you cannot send. Let's say you have 9 channels for a second order, and you say, aha, I have 9 loudspeakers, I'll just send each channel to one loudspeaker and that will work. No, this is not how it works. The same as it hasn't worked for the MS stereo. So we need to do something with that. So in terms of decoding, you have to actually make some sort of combination of these signals in the B format, usually all of them, and send this combination as a loudspeaker feed to each individual loudspeaker in your system. And this is not 2 or, I don't know, 4 or something like that, this is usually more. Although, you can actually decode ambisonics to anything. You can use it as mono. You can use the omni signal as mono and that's it, you're finished. Or maybe stereo, or some sort of surround, even binaural if you combine the ambisonics, because you know where the sources are coming from and you just need to rewrite it for the binaural reproduction with the binaural decoder. Or, well, different ambisonic setups, either just in a plane, in the horizontal plane, or spherical in full 3D. So you can, when you have the information, you can decode it to just about anything. For example, you can see something that we actually have in our lab. So 8 loudspeakers as a ring in the horizontal plane, and 4 up and down to add the height information, to extend it to 3D. What is important, I think I already told you to remember this for the MS stereo. So all ambisonics signals, W, X, Y, Z, all of them, all these components are actually used to create what we call feed, so signals for all loudspeakers. So you don't send just two of them here, just one of them there, you send all of them in some ratio. You gain a little bit of this, that, and you create a feed for this particular loudspeaker. How much you will actually take from each component depends on where your loudspeaker is. I will not go into this because I'm not ashamed to admit this is even above my level, so I'm not that much, I'm on the power user level, not a developer. So you need to know exactly where your loudspeaker is compared to you, to your speed spot. So it's 40 degrees there, 45 degrees up, and you even should actually enter the distance information to compensate if you cannot put it in a circle but in some sort of a configuration. So, to come back to our starting question, so how do we actually go about either creating or recreating a sound environment? Well, we can always do a recording. It will be an elaborate recording. We can do it, but in essence, it's the same as doing it with a simple single channel, simplest microphone. We take an octamic, an eigenmic, a Zilia, and we make a multi-channel recording of a particular event. Let's say it's a concert, or I don't know, me talking, but I don't know who want to listen to that in a special device. Anyway. But what we can do, we can do it for a specific microphone position. So my source is, let's say, here, I put it there, and this is a recording of that specific situation at that place at that time. And what we get in the end, after that conversion I spoke about, is B format ambisonics, which you can decode to just about anything if you want to listen to it. Or you can do measurements. You can take an ambisonics microphone and measure something that we call ambisonics impulse response. So something you would get with your Omni plus 3 figure of 8s plus all this other stuff, other components. So what is the advantage of that? Again, compared to the single Omni mic, you will know not only that the reflections, multiple ones from the room surfaces and everything arrive to your mic, you will also know where they arrived from. Of course, when you listen to anything like that, you will not hear each individual reflection, but that does not mean that the microphone cannot record it just that way and form the direction, spatial impulse response in the ambisonics format. And if you have that, you can always convolve it with any kind of dry signal, and you will get the impression, if you reproduce it, of course, on a 3D system, that you were actually in that room at the position of the mic, and that you're listening to a source that was placed exactly where the source you used to measure with was in the room. When it comes to production, you can always create this from scratch. So, on top of everything else that you normally use in mixing and recording, so the effects and everything, you can use something we call ambisonics panning. So you can place your source not only as in stereo, left or right, but virtually anywhere in space. If you say, my source is there, the ambisonics system should be able to create the right kind of those components, so W, X, Y, Z, and every other. When you listen to it and decode it, you will say, it really seems that my source is when I listen to it is somewhere there. So my guitar is there, my bass is here, my drums are behind me. Okay, maybe it doesn't make sense, but anyway. But you can actually do it. So you can synthesize your ambisonics environment. Or, of course, you can do a room acoustic simulation and say, give me the output in the ambisonics room impulse response, because I will use some sort of configuration, let's say loudspeaker configuration, to listen to it, to present it to my colleagues, clients, whoever. I could do it with binaural, but ambisonics usually sounds better. Don't ask me why. Maybe because you are actually physically present with the sound in the same space. You are not just experiencing it through headphones. Okay, and to finish, there is another very nice technique. Well, it's not actually trivial, but It's called wave field synthesis. So what's the issue here? Well, if you ever encounter, I don't know, a lab, a hall or anything, and you see something like this inside, so many loudspeakers closely together, you can be sure, or almost sure, that it's a wave field synthesis system. So what does this do? Well, the idea is to use these loudspeakers to create some sort of virtual source, either behind them or even in the room. I will show you how. By simply producing, each loudspeaker actually produces its own sound wave. It's an elementary wave, a little one, and all together they form a wavefront as if it was coming from that source you're trying to reproduce. I mean, a picture is worth 1,000 words. I will show you on the pictures what it looks like. So how is this done? Well, this uses something called the Huygens principle. So if you have a source, you have a sound spreading from it, propagating, you can define something called wavefront. If you throw a rock in the water, you see a circular waves spreading out. So each of these waves can be called a wavefront. And this guy Huygens, there was another one, but I'm not sure I know his name, says that each subsequent wavefront can be constructed if you say, this one right here is composed of many little sources, and each of them provides its own, let's say, sound. And all combined together, they produce the next wavefront, and the next, and the next, and the next. In practical application, these elementary sources, as I said, are loudspeakers, of course. This is why they are actually crammed close together. Actually, we have to have as many of them spaced as close together as possible. And to create our impression of the sound source, we have to be able to play with the delay and the gain of every signal on every loudspeaker to make it work. I mean, this is very, this is not practical yet. I will show you how it's done later. You could do it actually in full 3D, but then you would have to have the whole room virtually covered with loudspeakers. The floor, the walls, the ceiling. So this is not something we do because there will be probably thousands of them, maybe even tens of thousands. So what we limit ourselves to is usually to do this only in the horizontal plane. You see that all these loudspeakers are at listening level. Even with that, you could have anywhere from, I don't know, a few dozen to maybe a couple of hundred, or maybe even a couple of thousand if you are into it. So, to show you how this works, if the source you want is actually behind the loudspeakers, so it could be somewhere behind me, loudspeakers are here. So you see, we have a source that is supposed to emit sound in some sort of spherical fashion, and you say, this doesn't exist, by the way. We want an impression of that. So we want to recreate that behavior using these loudspeakers. So we say, this sound arrives here first, so they start emitting first, then these guys, then the guys on the outside. And each of these loudspeakers produces its own, as you can see, wavefront at the time. And when you combine all of them, I didn't even have to emphasize this. So when you combine all of these wavefronts, you get something, a recreated wavefront. It's not real. It is real. But the impression is as it was coming from that source, which doesn't exist. So this image was created using these loudspeakers. This is the basic idea behind that. This is the simpler, actually, part, because as you can see, this wavefront is actually convex. It bulges into space. So this is something that it should be easier to create. What is actually important is that the audience that is here, they say, based on this sound, I perceive a source that is here. It would be almost the same as if the source was actually here. But we used these loudspeakers to create a wavefront as it was actually coming from that source. That actually doesn't exist. So this is a virtual source. This does not exist. It was created by these loudspeakers. So this is the simpler part. Something more complex, I mean maybe more complex to understand, is that actually you can create a source that's in the room. So not behind loudspeakers, but in front of them. And this is actually a nice example. I was in a concert with a horn player who played with himself. So he was real on the stage, and he had a synthesized, well, some part of the song of himself playing on the horn. So one real, one virtual player were playing together. How can we do this? Well, to place the source actually in the room, what we need to do is to create not a convex wavefront, but a concave one, as if you had a satellite dish or a spherical mirror or something like that. So what does this do? You can see that first the outside plays, and they're a little bit cranked up to play louder. Then these guys, and then the guys in the middle. So this creates a concave wavefront. It actually focuses in this source, and then it propagates into the audience as if the source was actually here. If you have ever burned newspaper with the magnifying glass, then you might have noticed that you need to place it at a distance to have a focal point. If you are too far, then the focal point widens, as if the sound rays are actually coming from the focus. It's the same thing here. And the funny thing is that you can actually perceive this source very vividly in terms of actually being able to walk around it here and still say, oh, it's right next to me. There's nothing here, but you can hear it from there. The only thing that it's actually limiting is that you cannot walk here. So this area between the loudspeakers and the fictional source is actually off limits, because if you disrupt it, then all this is actually, the whole procedure is disrupted, and you cannot recreate the source that way. I mean, you can, but it will not be as sharp as it could be. So you cannot walk around here, but if you remain here, you will say, huh, I can almost hug the guy. It's right here. I mean, he. Okay. So this is actually my last slide. I'm a bit, okay. So this is very often used in research, and it's in what would I call experimental music production. Not everyone will have a waveform synthesis system, also for performances, as for some sort of virtual environment that you can create with synthesis. You can actually position any number of virtual sources. This is not limited to one. So for a single source that should be, let's say, there, I will have one signal processing, but I will add another here. It will be a little bit different. Something in the back, the third one different. You can put as many as you wish. If you want to do measurements, actually you can, but this has always remained in the sphere of research, because the number of input responses that you would actually have to measure is, let's say, in the range of the number of loudspeakers that you use. So this is not something that you would do every day. But there is actually one very big advantage over most of these techniques, and this is actually that most of these techniques work in a rather small area that we call sweet spot. You know it from stereo, between two loudspeakers. We have done it in our lectures numerous times. For those not in the middle between loudspeakers, your stereo image will hang to that side. So if you move a little bit to the left or maybe to the right, your stereo image just shifts right along with you. With ambisonics, it's even worse, because actually you come to the conclusion that you can only have a sweet spot as big as your head, or maybe not even for the high frequencies. So it's very, very sensitive. This one is not. So if you place a source, let's say somewhere behind me, all of you or most of you will say, aha, it's right there. And even if I move around the room, it will still be there at the same point, regardless. Yeah, okay. I think I'm finished. This was a little bit, I would say, tiresome because there is a lot of new information, but I just wanted to give you a theoretical overview of what can be done.